It is a pleasure to introduce our next speaker, Meenakshi Jyotis from the University of Oklahoma. The title of her talk is Isometric Rigidity of Projective Filling Currents.
Thank you. Thank you for the talk invitation, and thank you for everyone who showed up. Okay, so I'm going to talk about filling geodesic currents, which I'll define very soon, and I'm going to talk about its isometric rigidity, so a particular metric on this space of currents. Okay, so I'll start with, and everything in this this talk is joint work with Didac Martinez Bernal. Okay, so I'll start with the assumptions. All the surfaces so we're going to do two-dimensional surfaces, no dimensions higher. So all the surfaces that we're going to talk about are going to be closed, and they're going to be genus 2 or higher. So I don't want boundaries, so we're not going to think about surfaces like this with boundaries, or we don't want punctures either. And we want them to admit a hyperbolic metric. So admits a hyperbolic metric. And when I say closed curves, I mean closed curves are considered up to free homotopy. So closed curves are considered up to free homotopy. And when we are working with hyperbolic metric, all of these have a unique geodesic. So in hyperbolic metric, took up too much space, my pictures. So in hyperbolic metric, free homotopy class of a closed curve has a unique geodesic represented. Okay, so I use the word geodesic and free homotopy class of closed curves interchangeably through the talk. Okay, so the metric that we are going to define in this talk is going to be an extension of a metric that Thurston defined in Teichmuller space in the 86. So what is Teichmuller space? If you're given a surface of genus 2 or higher, you can also define it for surfaces with boundary. You're looking at all possible marked hyperbolic structures on S up to isotopy. So this is the picture I want you to keep in mind. You have a surface like this, and you're thinking about all possible hyperbolic metric you can put on this. So I have my Teichmuller space, so just denoted by this little ball. And for each such metric M1, so this is one possible metric structure you can put on it. So I have one element here, and like this is another, element M2, so I have another element here. And when I say marked hyperbolic structures up to isotopy, so what it really is, the equivalence relation here is we are going to keep track of closed curves. So if I think about this surface, this curve A, here, this is our A, this is our B, which is a short curve, but in this metric M2, this B is like elongated and you get a longer curve. And I have, let's say this is our C, and here the C is a short curve. So we want to keep track of closed curve in the sense that if I look at this surface, I really want to make sure like I'm not confusing, just twisting. Like the picture below is the picture M1 just like rotated around, and I don't want to count it as a different surface. So this is actually same as M1. Even though if without keeping track of the curve, it might look more similar to M2. So marking just means you are keeping track of the closed curves, and we are looking at all possible hyperbolic structures on a surface with respect to that. Okay. So there are several well-known metric structures in Teichmuller space. Oh, before that, okay. So this is a finite dimensional space, and it's finite dimensional because if you take a pair of pants, it admits a hyperbolic metric. And if you know the length of all of the boundary curve, so if you know the length of this L1, L2, and L3, that uniquely determines the hyperbolic metric on this pair of hands. That's all you need to know. So if you're taking a big surface, you can always decompose it in the pair of hands. But once you do that, if you know the length of these curves, L1, L2, L3, L4, L5, and L6, and if you also know, am I gluing these pans straight forward or am I twisting a little bit and gluing it? So there's something called the twist coordinate where we're asking, is this curve going like this? Or is it twisting a little bit and then glued? So if you know all those coordinates, you can uniquely determine the hyperbolic metric on a surface. And because of this, the dimension of the Teichmuller space is 6G minus 6. So this is what's called Winchell-Nelson coordinates for Teichmuller space. Okay. So it's a finite dimensional space, and there are three well-known metric structures, and one of those is defined by Thurston in the 86. So this is the metric that is going to be the core material for this talk. And what is this metric? So it's a symmetric metric, which is to say that if you take the distance from x to y, it doesn't necessarily have to equal the distance from y to x. So you can think of like a metric space with only one-way roads. So the distance from x to y and y to x is different. And the way we compute this metric is if you're given an M1 and M2, I can look at the geodesic representative of a simple closed curve and look at its length with respect to, so I'm defining d of M1, M2 with respect to, so this is Thurston metric, so called TH. So I'm looking at the length of a simple closed curve with respect to M2. Look at the length of a simple closed same simple closed curve with respect to M1. And when I divide them, I'm kind of seeing like how much is it getting stretched, like if I compare these two lengths. And then I want to look for the maximum stretch factor over all simple closed curves. Okay. Now, if you have M1 and M1 here, this would always be a ratio 1, and you could take supremum over all simple closed curve. It would still be 1, but that's not a good metric. So we'll put a log. And now if you put the same 1, all the 1s become 0. So this actually defines a metric on the Teichmuller space. So you can think of log of this maximum stretch factor. And it was a result by Cormac Walsh in 2014, where he studied this metric and he proved that if you take two different surfaces and you look at the Teichmuller space of both of the surfaces and you look at the metric, these spaces can never be isometric. Okay. So what we are going to do in this talk is we're going to extend this metric to a way bigger space, and we will prove this result for this bigger space occurrence. Okay. And the fundamental difference is that Teichmuller space is finite dimensional, and the space that we're going to work with is not. Okay. Right. So geodesic currents. So this is a space to which we are going to extend our metric. So geodesic currents were defined by Bonahan in 86. And to define geodesic currents on a surface, I'm going to first look at the space of all geodesics in H2. So what does this look like? So geodesics on a hyperbolic plane, so this is our point gradus model of H2. And the geodesics here look like either arcs of a circle perpendicular to the boundary or like straight lines passing through the origin. And if you take any two of these boundary points, I can always define like a geodesic passing through those. So the geodesics in H2 look like S1 cross S1 because I can uniquely identify this geodesic with the coordinate CD. But I don't want the coordinates that look like A8. They don't give me any geodesics. I'll get rid of the diagonal. So minus the diagonal. And I'm going to quotient by the relation AB is same as BA because we don't really care about the orientation. So this is a torus. I will get rid of this diagonal. And I'm going to quotient that by like folding it along the dotted line. Think of that as a crease and you're folding it and quotienting it like that. And when you do that, you get a Mobius strip. It's a nice exercise to see that this is a Mobius strip. And for this curve, let's say AB, you have like a point AB. Right. And you give it the topology of like a normal Mobius strip you get from a interval, a thick interval. Okay. Anyways, so we are going to define geodesic current on this space, of all geodesics. Okay. So if you're given a surface H2 mod gamma, so this is a hyperbolic surface. So it comes a cube with a hyperbolic metric, which is actually, this gamma is a subset of PSL2R. It's the isometric group of H2. Okay, so it behaves well enough with the metric structure on H2 that your surface comes with a hyperbolic metric. Okay, so what is a geodesic current on this space? Okay, so you look at the space of geodesics. This comes with our regular topology on a Mobius strip. And geodesic current is going to be a more Borel measure. So it's a Borel measure. What that means is that I can look at the Borel sigma algebra. So this is the sigma algebra generated by open. So if there is a topology, this is the sigma algebra generated by open sets. And I'm going to look at all possible positive, gamma invariant, locally finite measures. So mu is a measure that satisfies all of those objectives, and any such measure like that is a geodesic current. And the place where the surface itself comes to play is this gamma. So that's how it's related to the surface. Okay, and locally finite means if you take a point, you can find a compact neighborhood with finite measure. So we look at the space of all such possible measures. That gives you the space of geodesic current. We give it a weak star topology, and I'll denote the space by CFS or just C. So it's interesting because there are a lot of interesting objects that sits inside the space of currents. One of them is if you take any closed geodesic, it's an element in the space of currents. Tacmular space admits into the space of currents. If you heard about measured laminations, that admits into the space of currents. People study flat structures, especially people who study things related to dynamics, so that is also a subset of the space of currents. Okay, so we'll see a few examples, and the easiest example to see is that if you take any closed geodesic, it doesn't have to be simple, it will always give you a measure that satisfies all of these nice objectives. Okay, so if you take a simple closed curve, I'm going to draw a simple closed curve. You could draw a curve with how many over self-intersection, and the same thing would work. So I'm going to draw this curve, and if I'm going to look at all of the lifts of this curve on H2. So I have one, two lifts up in here, and there's like more. There's infinitely many lifts, and I'm going to look at G of H2, which is her Mobius strip. And it will give me, each of these lifts will give me a point, And it's a proposition. It's not trivial. It's not easy to see. But if you start off with the closed curve, all of the lifts will always give you a discrete subset. Okay. Again, it doesn't have to be simple. Okay. So once you get a discrete subset, I can define, this is gamma, let's say. I can define a measure called mu gamma, which is a counting measure. So if I take a little open set U here, mu gamma of U is just going to count how many of those dots are there. So this is going to be 2. Yeah. So because of this, every closed geodesic or a closed curve up to homotopy is a subset of the space occurrence. And Monahan proved that, in fact, if you understand closed geodesic, you understand the space occurrence. So if, let's say gamma is a closed curve, you get a measure mu gamma. If you have a measure, you can multiply your favorite real number and you can scale it up. This is what gives examples of weighted closed curves. Again, give such measure positive weights, but that is dense in the space of currents. To understand currents, this is all you need to understand. Another example comes from Liouville measure. So Tegmark space embed, so for every M1, every metric on Tegmark space, you get something called a Liouville measure on the space of currents. I'm not going to do the construction because it's fairly technical. And the nice thing is that not only does all of these things embed into the space of currents, they interact pretty well. So say for example, if you are given 2 closed geodesics, let's say A and B, there is this notion of intersection form. I'm going to denote it by I cap because I want the I for something else. This actually counts how many times these 2 geodesics intersect. And this in this case is 1, so this is the geometric intersection number between 2 closed curves. And this extends to what's known as intersection form on currents. So intersection form is a bilinear form from currents cross currents to R. It's continuous. In fact, intersection is always going to be positive. It can be 0. So it's bilinear, so you can add measures and you can scale measures. It's going to respect that. And as you would expect, if you take 2 closed curves, you can think of the currents you get from those closed curves, and the intersection form agrees with the geometric intersection number. But the nice thing is, if you take a metric from a Tegmark space and a closed curve, and then you look at the Liouville measure from that metric and the geodesic current from the closed curve, you get the length of the geodesic. So it interacts well with other structures too. All right, I have like 5 minutes, I think. So I should define the metric. All right. So to define the metric, I have to define first what's called projective currents. So the space of currents is huge. It's not finite dimensional. It's not compact. But a way to make it compact is to look at, so this is all, you can take a measure and give it whatever positive weight, but I'm going to quotient it the scaling. And when you do that, we get what's called projective currents, and it's a compact space. So Tegmark space embeds into the space of currents, but it also embeds into this space of projective currents, which is nice. In fact, flat structures also embed into the space of projective currents and give it a compactification. And when you do that, what's on the boundary of Tegmark space is what's called PML, or measure laminations. So measure laminations were defined by Thurston long before Monahan defined currents. But one way to think about measure lamination is that weighted, it's not the definition, simple closed curves are dense in measure laminations, and this is the projectivization. So weighted closed curves, all closed curves are dense in current, but if you restrict yourself to simple things, that is measure laminations. Okay. And this is what is called as the Thurston compactification of tegumental space with the boundary of PML. Okay, so we want to define our metric on this projective wise version of currents. But there's one more thing before I get to that. So when you look at the space, I have the space of all projected currents. So on the interior of the space is what we have as called projective filling currents. And on the boundary is projective non-filling currents. Okay. So filling currents are currents which have non-zero intersection with everything else. And we can projectivize it. That will give you the space of all projective filling currents. So this is C fill of S up to scaling. Okay. And the metric that we are going to define is going to live here in filling current. So it's extension of tegumental space because tegumental space still sits inside. So Thurston's algebra metric was defined here, and now we're going to extend it to the whole space. All right, so what is this extended metric? So this is to recall what Thurston did. So the extended Thurston metric. I'm going to look at two currents. Let's say mu nu belong to currents. Our extended Thurston metric is on filling currents and projectivized version of it. So I have to take the projective class of mu and projective class of nu. This is, so I'm going to do what we have here. So we saw that the length is actually intersection form. So to extend it further out of tegumental space, I'm going to define mu gamma. Have second thing goes on top. It's a convention, you could do it either way. Mu gamma. And now instead of taking supremum over all these simple closed curves, which is not enough to understand current, I'm going to take supremum over all closed curves. And I'm going to take log of this. Okay. Now there is a problem with this definition so far. The way I have written is that I took a whole projective class, but intersection form is only defined at the level of currents, not at the level of projective class. So I made a choice there for a current in the projective class. So to make it well defined, I have to normalize it with what's called entropy. And now we have our measure. So this actually follows from the work of a lot of different papers. It was never put together on what this is in the context of currents. So recently, my collaborator and I, we put it together in the context of current, but it doesn't feel like we defined it because it kind of existed before. Okay, and this H is called entropy, and it's really here to normalize because H of nu is 1 by k nu, and I of nu gamma, H of k nu. 1 by k nu. I of k nu gamma is k times I of nu gamma. So it kind of cancels out if you take any other thing in that projected class. It makes it well defined. So what we prove is that if you take two surfaces, different surfaces, and if you look at the space of projective filling currents with respect to this metric, they cannot be isometric. The surfaces are different. And also, it was a consequence of actually studying what is the Horo function compactification of the space. And it turns out for PC fill, the Horo function compactification. So if you haven't heard that word, it is very useful, but if you haven't heard it before, it wouldn't make sense. But this metric helps you to distinguish space of currents. That is my talk. Thank you.
Thank you for the nice presentation. Let me stop the recording.